Okay, this thing is recording, right? Okay. Hello, everyone. My name is Tishaton Jungcham, your friend from physics. You can call me Katua if you want. And I'm here to talk about my senior project, which is Thailand's province temperature variation and epidemic suitability of Aedes mosquitoes. In Thai, we like to call them Yung Lai. So I'm not here to talk about what a mosquito does to a human being. I'm not here to talk about that. That's not physics, that's biology. But let's know that when I talk about dengue viruses, I'm talking about ไข้เลือดออก Now, our objective for me is that I would like to find the temperature influence on Thailand's province, the epidemic suitability, if you will, and the geographical risk. So by going through Thailand's province and their temperature variation regimes, I should see that each province have their own suitability. And finally, I would like to create a standard simulation model of that epidemic that each province have. In order for us to start, we need to know about the compartmentalized model of transmission. When we talk about a compartmentalized model, we have to think like we're an epidemiologist. We need to separate human and mosquitoes into human compartment and vector compartment and identify what class they are. Now they are basically the same, S-E-I-R, except for the exception of R in V. I would like to reiterate something. The V is vector for mosquitoes, the H is human. So there's S, susceptible, E, exposed, I, infectious, and R, the recovered. We assume that mosquitoes remain infectious until the day that they die. Now, the way that things work is that mosquito isn't born with a disease. They have those disease because they bit infectious human, like this. From here, they bit an infectious human to susceptible vectors, and then they become exposed over time. And just like the same, humans are not born with disease, they only get the disease by the disease-carrying mosquitoes. So they got bit by mosquitoes. That's why they changed from susceptible to exposed, then infectious, and then recovered. Now, the way that things work is that we need to understand the dynamics of how temperature influence these variables. Based on the paper that John H. Huber used, which is a paper by Aaron A. Mordecai, detecting the impact of temperature transmission of Zika, dengue, and everything else. They actually record every temperature-dependent variables into form of graph. They record in a form of graph, which is a quadratic formula and a Bria function. Basically, one is a parabola and one is a bell curve. And you'll see in a bit what it represents. But they record the behavior through temperature of the mosquitoes, through biting rates, egg lays per female per day, the probability of mosquito eggs to adult survival ratio, and mosquito eggs to adult development rate, adult mosquito lifespan, probability of mosquito infectiousness, probability of mosquito infection, and virus extrinsic incubation period. Now, I say this because I want you to know that these are all the temperature-dependent variable, but there's also a temperature-independent variable that we have to consider when it comes to this epidemic. But first, we need to sort this thing out in form of quadratic and Bria function, which has already been recorded. We just need to, reuse all the parameters again, which they already have for us, which is Tmin, Tmax, and C, as in like scale variables, just for scaling. Change the slide. As you can see, I have graphed it out for us, and then we can see that the biting rate, let's say like at 10 degrees Celsius, mosquito doesn't bite people. They don't go around biting people. But when it's at around 30 to 35, that's the highest, the ideal temperature for mosquitoes to go around and bite people. Same goes for everything else. We could take a look at this, and then we understand that every condition has their ideal temperature for it to behave. Now let's talk about temperature independence parameters, which is the intrinsic incubation period. Intrinsic incubation period and extrinsic incubation period is different because extrinsic is when the virus or the parasite or anything builds up in the carrier, which is in this case the mosquitoes. But the intrinsic incubation period is us. When we get bitten by mosquitoes, we have the virus inside us, but those virus does not multiply and replicate enough for us to transfer it to other objects like mosquitoes or people. So that's why we have to wait for the intrinsic incubation period for us to become infectious. And there's also the human infectivity period. We become infectious, yes, but then over time, those viruses will die out, and then people won't get virus from us anymore. In this case, mosquito, if they bit us, they won't get the disease. That is around 5 days. And now we also have the proportion of initial infectious human in a scenario. So I have to say that in our simulation, we have a constant amount of human. So the SEIR have to be added up into the same amount of population. In this case, I think we use 10,000. So since this is 0.0001, we have the initial infected individual as 1. Why, you may ask, is because that we would like to replicate a dynamic in the most fundamental ways. As in, like, yes, we could adjust this number to be lower, but then it would take more time for the virus to spread in the simulation. And if we added more, then the virus would be too rapid. And then we can't, take a look at the data. Proportion of initial infectious mosquito, we set it to 0.015, which means that there would be, if there's 1,000 mosquitoes, 15 of them would be infectious. It's the same for the human population to replicate the dynamics in a realistic ways. And last of all, the ratio of mosquitoes to human at 29 degrees Celsius. The ratio of mosquitoes to human, if human have 10,000 at 29 degrees, they would have around 2,000. Right, 10,000, they would have about 20,000. We'll talk about this later because this is the ideal temperature that we're going to use for later on, which is the carrying capacity. But first, we need to understand the ordinary differential equation that would discuss the relationship between mosquitoes and humans. So moving on first to the vectors, or the mosquitoes, the ordinary differential equation, using the temperature dependent variable, we could see that they have their relationship of the standard susceptible mosquito. Where do they come from and where do they go? We consider the susceptible by the birth rate, which is the eggs laid, the amount of that egg that would survive, how much time it would take for those eggs to grow, and how much would die out over time, compares to the initial mosquito that we have throughout the carrying capacity, which we'll talk about later. Like I said, the carrying capacity will be the logarithmic growth that set up the trends on how much the environment would allow the mosquitoes to be in. And the only way that the rate over time that the mosquitoes would lose their susceptible class and becomes exposed class or something else is throughout that they would bit on an infectious human. Like I said, like we said about, so how much they would bite as like their biting rate and how much those bites would cause them to become exposed. We threw out the human over all the throughout the infected human over their population. Also, we have to consider that the mosquito died out too. We don't do that for human because epidemic could last for like a year, but human life could last for 80 years. So, that's too long. So we don't consider about the human lifespan, but we do for mosquitoes because they only have a lifespan of around 24 days. Anyway, they changed class to expose through biting infectious human and getting those diseases. And just like the same, they would change class from exposed to infectious only when the extrinsic incubation periods kicks in, which is when the virus builds up inside the mosquitoes and make them become ready to transfer the disease to other susceptible humans. Also when they died out, so, grade one. Lastly, the infectious mosquito, they would only change class when they die because we assume that the mosquito would remain infectious until they die, right? Right? Remember? Good. Okay, moving on to the carrying capacity. Moving on. The carrying capacity, like I said, is the maximum population, the population size of the mosquitoes that the environment allowed. Mosquitoes to be over system. Let's say, what did I wrote? Maximum population size of mosquitoes that the environment can sustain at a given temperature. It is a modified Arrhenius equation, which actually says a lot about, which is an equation that would explain about the behavior and the, what is that thing called? Reaction rate through temperature. So, we use our Boltzmann constant and everything for that. By considering all the temperature dependence variables and the Arrhenius-based equation on this side. So remember when I said that the ideal temperature for mosquitoes to be twice of the human is 29 degrees Celsius? Yes, the ideal temperature is what we'll use for reference temperature, which is the T naught. So every time you see a T naught, think of it as 29. And don't get confused between NM with NV or NH. NM, in this case, is the amount of mosquitoes in the reference temperature, which is, remember, twice the population size. So NM in this case, I should have right, but I didn't, is 2 times NH, combine the sum of humans in the area, in the system that we use. And also the Arrhenius equation, EA is activation energy, T is any temperature that we going to use compared to the reference temperature, which is, say it with me now, 29. Over the exponent of Boltzmann constant plus the reference temperature and the temperature in terms of kelvins. Basically, that's what carrying capacity is. Do anyone have a question? Nope. Then we move on to the human. Now, for human, it's a bit funny because we have to consider also the temperature independence variables. So now, sometimes those temperature that we have to change from time to time have a constant amount of variables, such as parameters, such as incubation time or recover time. Remember 5.9 and 5 days? Anyway, so just like mosquitoes, we have a finite amount of human. We say that we have 10,000 human in the area. So susceptible humans would only lose they would never get more susceptible. They could only lose susceptible human over time. because if they get bitten once, they change class, and eventually they end up in the recovered class. And since we are using a constant amount of population, we never get any more human in the systems. Anyway, that's why this thing is a negative, because we only lose them over time. Let's say how much the human in the area would get bitten by the mosquitoes in human population, the biting rate over the mosquito in the area, and what's the probability of those bites being infectious, B of T. That's the change in susceptible human over time. And then eventually, since we're losing this much amount of susceptible human over time, that means that we're gaining this much exposed human over time. And the only way that we could lose the exposed human is throughout the incubation time, which is 5.9 days. And then again, yes, once 5.9 days develop, they become infectious, could transfer to susceptible mosquitoes, but they could only do that for 5 days because of the recovery time. When they recover, nothing happens. They become recovered. And then we consider that the simulation would end. They won't get bitten ever again. Okay, thanks. Okay, now, that is why I would like to point out that the temperature throughout the changes in temperature would matter. But first I need to show that constant temperature also have an impact on the dynamics of this epidemic. So, what if I were to tell you that, hey, I have a temperature of 20, 25, 30, and 35, the same throughout 365 days? What would happen to the equation that I just listed? Could you go back to the equation? These equations, the temperature dependence variables and the change of class over time. What would happen to the human? Every class of the human, and not just human, because we have to also consider the mosquito, the infectious mosquitoes. That means that we also have to use the constant temperature inside the vectors, or ordinary differential equation, to answer for the human ordinary differential equation. Okay, get back to the same slide, please. Thank you. What we discovered is that temperature acts weirdly when it comes to some form of temperature. So at 20 degrees Celsius, in the susceptible class, basically almost no one get bitten, and then they remain susceptible for the rest of their lives. But when it's at around 25, that's when you see a huge impact, where about 94% of the human population that we have, which remember we consider as 10,000, 94% of them become infected, becomes exposed. We only consider this thing first, okay? We'll get to the other one later. And the worst of all is the 30 degrees Celsius, which is almost roughly about 99.98 people become exposed to the infectious mosquitoes. While at the same time, when temperature goes higher again at 35 degrees, they drop down to 5%. What's going on there? Well, we can see that the susceptible humans is basically an inverse of recovered human, because they have the finite amount of populations, yes. But that's not what we focus on. What we focus on here is this, the exposed and the infectious compartment. Now this compartment shows how much people would be infected over time or become exposed over time, which is daily. Yeah, this is in terms of daily. The maximum amount of people infected over time is 1,500 ish for that, and 1,200 for that. So at 30 degrees Celsius, you can see 30 and 25, you can see the most sustained outbreak in the epidemic. Just like this. But the difference between 30 and 25 is that 30 degrees Celsius is very rapid and it ended abruptly. So it rise and then stop. But 25 degrees Celsius is a slow spread. But they slow spread, but they doesn't spread as rapid as the 30 degrees Celsius. So for the viewer in here, let me ask you this. Which one do you think doctor would prefer, a rapid spread or a slow spread when it comes to an epidemic?
Slow.
Slow spread. Yes, you are indeed correct. The slow spread would be preferable because this, you could take actions in time. But when a rapid spread happens, you can't take measurements or anything. People would, people would die out. Anyway, moving on. This is only just to point out the constant temperature over time. But when we think about real life, you might say, Ketua, come on. Temperature is not going to be 20, 25, 30, 35 all years. Temperatures change daily. That doesn't work. So I hear you, and I agree. And I would say, sure, but we can't replicate a real life temperature. So what we can do is first introduce a seasonal forcing, which is to replicate a sine wave in order to make a daily changes in temperature. So what we have here is an equation for the seasonal forcing, which is the T max minus T min over 2 multiplied by sine of 2 pi over 365T plus the T mean. Now, with these combinations, I could replicate a sine wave temperature for, let's say, areas globally. That was hard to pronounce. Such as Sao Paulo in Brazil and Shanghai in China. Yeah, okay, Shanghai is in China. So it's somewhere that looks like this. You can see that Shanghai have a very high amplitude, but a very low mean temperature. But Sao Paulo have a high mean temperature, but a low amplitude. And in order to show you the difference, I have made a graph which looks like this blue and red line over here. Basically, you can see that the high amplitude is very oscillating, and the low amplitude doesn't oscillate as much. And what would happen if we were to run this through a simulation again? Well, we'll get to that, but we need to understand what seasonal forcing basically tells us. If I start my day at the first of the line, then the second day would go higher. Everyone can see that, right? And it would go higher until it reached the maximum extreme point and then drop down to the minimum extreme point. So if I were to make a daily graph, the equation would look somewhat like this. This. The T mean plus A, which is the amplitude. The amplitude is the T max minus T min over 2. Multiplied by sine, same thing. But instead of just T, we have T plus T naught. Because remember, eventually it would end up right in the same place. If I want to start my temperature at 25, eventually they'll end up at 25 again in the future, 365 days later. Here's a Desmos explanation. If I want to start my temperature at day 1.08, I would have a temperature of 25.28 degrees Celsius. Yes, and then 365 days later, I would have the same temperature at the day 366.08. Now, what I want is I want day 1, day 2, day 3, day 4. So I need to extract data of the temperature of day 1, day 2, day 3 until 365 days. So say I have an amplitude that have the maximum temperature of 40 and the minimum temperature of 10 and the mean temperature of 25. I want to start my temperature at 15 and it will go up, and then it would drop down. So what if I start at 25? Okay. So what if I want to start at 24? Then it would end up somewhere around here. And then the day that it dropped down would be earlier than the 15. And you guys understand this? Right? Got any questions? All right. And you guys are synchronized. You're like, anyway, moving on. So when we were talking about the starting day, remember the 15 and 24? Now we create a graph that the starting day becomes from 10 to 40. So this thing is the starting temperature, just like the previous graph. You get back? Remember, starting at 14, then we run through the simulation through daily temperature. So this day 1, day 2, day 3, day 4. Okay, moving back. Same goes for this thing. So I start at 10, 15, 20, 25 until 40 and see what happened. These things have been run for 365 days. So as a result of 10 degrees Celsius, almost nothing happened. No epidemic occurred at all. And no final epidemic size because there's enough for mosquitoes to survive. But when the temperature is at 10.25, remember the next day it would be higher, 10.25, 10.5, 10 point blah, blah, blah. Then the epidemic happens, and actually it happened very small. So the maximum number of infections during the starting day of 10 is small but sustainable. That's why the epidemic is almost the highest at around 140 days. So if we continue that on until around 35, I mean the maximum of 24 of something, we can see that they have a final epidemic size that is very high comparable to the number of infections. Let's say this is the peak. The epidemic length would be somewhere around here. It is sustainable, but then the human in our compartment would run out. So, they get bitten way fast and gone. Now, that's when the maximum temperature is 40 and the minimum temperature is 10. What about if we change that? We still have the mean temperature of 25, just like the previous graph, but now the maximum temperature, we narrow it down from 30, from 10 to 40 to 20 to 30, let's say. Then we have something that looks like this. Now remember, from our constant temperature graph, right? The 20 to 30, the 25 to 30, that's basically an ideal temperature for an epidemic. So when it narrows down the graph, basically that means that the temperature is likely to stay at 25 to 30 more than the y graph from 10 to 40. So 20 to 25 only stays for like a little bit, but 20 to 25, 25 to 30 in here stays for a very long time. So the final epidemic size is like a monotonic relationship that almost 100% of people are infected. And the maximum of number of infections are basically like this. And the epidemic length just decreased down until probably around 29.4. Then you see it spike up. Moving on. Now we do that again, but now we create a heat map from it. From what we have is that we have a sine wave seasonal forcing. We did that to the degree of maximum temperature of 10 to 40 and maximum temperature of 20 to 30. But this time, we widen the range of the amplitude. So if it's 10 to 40, then we have like an amplitude of around 15. And if it's 20 to 30, then we have an amplitude of 5. Because remember, T max minus T min over 2. I'm not going to do a calculation over here. But still, so that's what amplitude basically means. If the amplitude is high, that's kind of like 20 to 30. This one's kind of like 10 to 40. We widen it out. And also down here would be the annual mean temperature. Annual mean temperature. So basically, the previous graph that we did, we have 25, but now we widen the area up from 10 to about 38. And this thing is about 0 to 17 amplitude to reflect global temperature scale, the possible global temperature scale. And what we can see is that there actually is a band for where the final epidemic size would happen. So if we go back to the previous slide again, the final epidemic size could be calculated as in what happened at the last day when we take a look at not this graph, but Jai, could we get back to the previous graph, the constant temperature? Okay, constant temperature. The final epidemic size could be calculated at the final day, the day of 360, when we look at the RH. We can see that they change over time, but at the last day, here's where it's going to be. So from 10,000 people, 99% infected, and then 94% infected, blah, blah, blah. We only take a look at the final day, which is the day 365. So get back to the heat map. Yes, now heat map. So the final epidemic size could range from 0, no epidemic at all. So the RH at the last day doesn't rise up, kind of like the 20 degrees Celsius, and the constant temperature could go up to 100% around here. So when mean temperature change, they could support a finite amount of amplitude. So high amplitude, high mean, low mean, high amplitude, something like that. This is in terms of heat map. So that's basically what the paper in the John H. Huber did. So what can we do with it? What can we do with the information? Well, we have that monthly reported temperature in Thailand for each province, all the 77 provinces. What we can do is that we can average it out into a single digit of temperature range and temperature means. And then we plug it back into the previous heat map and zoom in so that we would get this. This is basically the same graph, but instead of the ranging from 10 to 38, we have range from 22 to around 30. And the T range, basically it's amplitude, but I don't divide by 2. So if I have to compare this thing to the previous amplitude, this one would be around 6, and that would be around 4. The T range for every province in Thailand could be seen. But remember, Thailand, could we get back to the heat map? Could we get back to the heat map? Thailand is only somewhere around here. So we're already in the red zone. So it's very, very hard for us to determine the final epidemic size if we go and to compare it from 0. So once we get back to heat map in Thailand, we have to range from 0.99 to 1. Essentially a 99% in every province. But which province is in the safe zone? Well, it's Pichin. And which province is at the danger zone? It's a surprise, it's Yala and Narathiwat. And yes, even though we scale this thing down into like 0.99, 0.99 is over here. So Pichin is somewhere like 0.998% final epidemic size. So, scale it up again and then individually color-coded each province into their compartments, and then we get this color, as in Pichit to Narathivas in this color scale of 0.998 to 100% final epidemic size. And what we did is that we used this color to plug inside the Thailand map, and then we get this. Okay. Yes, we get this as a Thailand map for the seasonal forcing with an epidemic suitability at the same size. So what can we do with this information? Are we done? No, we are not. We have to check if this data is accurate or not. So we have to compare with an actual reported case. So an actual reported case that we have is this. A cumulative case is a monthly reported amount of infectious case that people report in a hospital, and then I add them all up into its annual report compared to the size of the population in each province. So I would get something that looks like this. A cumulative case ratio, and this one is an annual cumulative case ratio. Case over population. But I'm only going to make a map from it. So yeah, I have to average all of this. And what I get is this. A cumulative case ratio per 100,000 people. So each 100,000 people, about this amount of people would get infected. So in this province, I don't know what it is, I would get around like 100. And somewhere around here, they would basically get a digit of the report. So basically not that much. So could we use this to compare it to the seasonal forcing? I mean, yes, but because I have time spare in my hand, we also do some interpolation technique, which is instead of doing seasonal forcing, replicating a sine wave function, we use an interpolation for each month. Because we have a monthly reported temperature, now we could replicate a daily temperature by using the equation, the temperature of this month, the month that we're using, plus the next month minus the month that we're using, multiplied by day minus 1 over the number of months, the day that that month has. So let's say if I have January, let's say we got to do January, then we have to use our reported monthly temperature on January to be plus February minus January. So that's going to be the slight daily shift. But in order to do like a daily shift, we have to know like what day of the month we're using. So at day 1, day would be equal to 1, and then divided by the number of months. So the number of months would be 31, right? 31 for January. So that would be the first day. And we do that until this is 30, until the day is 31. So it actually increased rapidly. I don't know if I included it in the slide or not. But yeah, let's try moving on. Change slide. Okay, here's an example of the mean Thailand province. Now I do temperature, mean temperature, maximum temperature, and minimum temperatures. And what we have is something that looks like this. Basically, from what I said, this is the months. Yeah, this is the months that we have, the average months spanning from 2009 to 2018, because we don't want COVID, and we only just want to range for 10 years. So from this, we get this as a daily temperature. Remember, we're converting monthly temperature into daily temperature. So in terms of T-mean of Thailand's province, we have 365 columns of information that looks like this for each province. in the temperature mean. So I replicate it because I need to loop it, not just 365 days, but I try to include, I try to replicate it thrice. So it's actually 1,095 days. So basically divide this by 3 first. This happens in a year. So in Grum Thep, we would start off at somewhere around here, and the temperature month 1, month 2, month 3 continuously rise and then drop down, and eventually end up right here at the bottom, which is the end of the year. But because I want to loop it again, I just do it again 3 times. 3 times, 3 times, 3 times, 3 times. For Amazon, Grum Thep, Chiang Mai, Yala. Remember, I'm doing this for 77 province, so I'm not going to include this in the slide, but I'm just here to illustrate this for you guys to see that each province daily mean temperature is vastly different after doing interpolation. So I have a change in daily temperature now. Not using seasonal forcing, not using sine wave, but an actual data that replicates in real life. So I run that throughout the simulation again, which is the ordinary differential equation. And then I get something like this. Remember, I'm comparing this to seasonal forcing, epidemic suitability, and Tmax, let's say January, Tmean January, T minimum January, because we have to do all the 12 months. I'll talk about that later. But the epidemic suitability, remember, this thing is 99.8% infected at the minimum. So when I scale that down to a 0, this thing practically became red. Same goes for the T mean. Yeah, the T mean between these two. It practically becomes red. But that's only because I run the simulation at the first day as January 1. I have to do it in every single month. In this case, I only did for January. I'm not done yet. I still have to finish this simulation. But for January, if I run in the first day at the mean temperature, I would get a very red epidemic suitability, which is basically epidemic suitability is the final epidemic size. It's the same, but we just changed the name. And the temperature min, some of the province doesn't get infected at all. While in the epidemic suitability across Tmax, some temperature is actually safer than other temperature and than other areas. So, could you click that 2 times? Okay, so the reason that I have to do this is because that I didn't just run it through 365 days. I have to run it until the amount of infectious the infected human becomes less than 1. So the final size would be somewhere around 0.99%. So here's the data it would run. The epidemic length would cause for spanning from 165 to 249. Remember, there's 77 provinces, so there's a lot more information. Same goes for the maximum temperature. But here's the funny thing for the minimum temperature, because it's very low, that actually the epidemic is sustainable, that it over exceeds a year. Can you click that again? Sometimes you can see that it could pop out more than 365 days in here. 365. I actually finished this simulation already. So yeah, this information is very old for me. I will change that in my senior project. But you see, when it's finished at 365, the final infected human is still very high. So that's why I have to run the loop 3 times. Remember what I did? Yeah, I need to do that. This is before I put on that graph. I should have included in the slide. Same goes for seasonal forcing, but I have to finish this first. But let's say that I did that 12 times for seasonal forcing, the maximum temperature, the mean temperature, the minimum temperature. I have all run throughout all the months. I have to add them all up and divide it by 12. Basically, I have to average them again to get their average final epidemic size, final epidemic suitability. So let's say I have a hypothetical data of the average Tmax, Tmean, Tmin, and seasonal forcing, average throughout all the 12 months. Can I compare to my reported ratio now? The answer is no, it cannot. It's not the same, at least not yet. That's why I had to do a statistical analysis through Z-score transformation, which is essentially just the mean of those information divided by the standard deviation. Very simple analysis. But because of the reported ratio missing like 5 problems, then I have to exclude those 5 problems for every single method that I use. The seasonal forcing, max, mean, min, excludes 5 of them. And when I go through all the Z-score transformation, then I would get something that looks like this. A very comparable at the same scale information that could later on be used as a mean square errors measurements. Something that looks like this. We have a mean square errors of every province, and then we average them for the last time to have this. In this case, the one that I hypothetically made, the lower the number of the MSE means that the more accurate it is to the reported ratio. So in this hypothetical case, the average minimum temperature is the best simulation to use it's the best method to use in the simulation. And here, let me graph the Z-score for you guys. It would look like this. Everything would be in the same scale. So even though the color is different, everything is in the same scale. You can see the 5 missing province in here. Oh, and just to be sure that I do this mathematically right, I also made like another R program, just to check the mean square errors. And that would be the end of my project. So it's not done yet. But I'm close. I'm very close. Okay, anyone have a question? Yes, sir. Ask away. It's SH. SH is
population of humans.
you. Okay. Sorry.
SH is the population of humans.
Yeah, it is.
So I think for this ODE, it just decreases human population.
Yes.
So, but I think in reality it must be increased and not the infected human population too.
Oh, you mean there should be more human being born, right?
No, I thought we have to add another increasing term for SH.
What do you mean by increasing time?
You mean
Because this equation just say biting rate, right? So it's obvious that the SH is just decreasing.
Yes, only decreasing, because everyone in our system, we have 10,000 people, 9,999 of them is susceptible. So there's only 10,000 people in the system. We're not using like reality, where there's going to be people being born or people dying. We only assume the number of people to be 10,000 people.
Yeah, but normally we can escape from mosquito, right?
Yes, nobody can escape from being mosquito. Once they get bitten by mosquito, they become recovered and they don't move back to being susceptible.
Also, in your model, you don't consider escape.
What do you mean by escape? Like
It's like a go. Like sometimes you can escape from mosquito from just go inside or like put the mosquito avoiding medical or something. Yes. No, no, we don't. We don't consider that at all. We only try to simulate a case where an epidemic were to happen, and there's no consideration of like humidity, no consideration of immunity, and there's no consideration of like people being wearing like having protection against mosquito, so they're 100% vulnerable.
Hello, I can't hear the audio.
Wait, is it muted? Oh no. Okay, that was 3 minutes ago. So basically what I have to reiterate is that the final epidemic size is the recovered class at the final day. So when people are infected, they become recovered after the recovery period. And at the last day, at the day 365, we calculate that and use it as, we record that number of recovered human and use it as the final epidemic size, basically.
Oh, I have a question.
No, it just said that you're muted. It's a mute, sorry.
I have a question.
Yeah.
Is it considered that only female mosquito bite human?
Yes. I didn't write it down, but only female mosquito is present in this simulation. It's already written down in the, I think in the temperature dependence variable. So wait, hang on, I'm gonna go back to the slide. Okay, so basically the biting rate is considered as to only be female. So it's already in that probability, I think.
Does that affect population size?
Population size of mosquitoes, right?
So is the population just female only?
Yes, just female only.
Okay, thank you.
Yeah. All right, so I think we're done. Are we? Are we done? Yeah. Yeah. Why mostly? Why mostly? You mean why is it depending on temperature? I know there's mosquito. Mechanism of mosquito. If the weather is too hot, they don't bite people, and if it's too cold, they would bite people, but not that much. They won't have the energy or anything to. No, we could go for a graph, and then we could like go over this thing real quick. Right. So okay. So the biting rate, they don't have energy to bite because it's too cold, so they can't bite as much as like the prime time or around 30 degrees Celsius. The mosquito would be super energetic and it would go around biting people. This has been experimented and recorded by Aaron A. Mordecai. So yeah, we're using their recorded information. Someone have to. You mean Aaron A. Mordecai? My work further. Any aspect that you think should be improved in the future is that is a very good question. Okay, so because of my research only depending on temperature, there is so much parameters that we could consider, such as the humidity level of Thailand, which we could also do that, but then we have to modify our ordinary differential equations. So it's going to take a lot of time. We could also invest it on immunity levels, which is something that Rahul suggested. And it would be amazing for the simulation to replicate on how the dynamics would work on the epidemic. But other than that, I think there is a lot of more things that we could invest it in, but I can't think of one right now. Humidity, immunity. What else? Do you guys have any suggestions? How about you use your model to compare structural data of malaria? Oh yes, I could also do that, but like isn't malaria is from other strains of mosquitoes. The one that we're doing is called an Aedes aegypti type mosquito, which carries the disease dengue, Zika, and chikungunya. So yeah, even the paper from Erin A. Mordecai is doing Aedes aegypti. If I change the phenotype of the mosquito, their behavior and their temperature dependent variable would change along the way.
That's what I wanted to ask.
Yes, sir.
Because the model is seem to fit for anything like the same parameter. So besides, so if you change the phenotype of the mosquito, would there be anything else that changed aside from the numerical value of each parameters?
Very good question. I haven't explored on other aspects, but assuming that we're changing the phenotype of the mosquitoes, not just the temperature dependent variable, the parameters would change, but I say it would change also to the ordinary differential equation in the more advanced ways. So from what I do is SEIR, a normal, like if you get bitten, become recovered, and then you never get bitten again. But from what I said to water is that we could, in reality, dengue, you gain immunity for 6 months and you become susceptible again. But at the meantime, you're immune to like 3 other phenotypes. If you change the phenotype from Aedes aegypti to the one that carries malaria, then yeah, those ordinary differential equations would change. But it would still be applied in my SEIR because it's just standard model. Oh no, Anat's gone.
I don't understand this. So you try to compare the mean value and find the C's or to see if they are different like that. Make sure that.
Oh no, it's because of the cumulative case ratio. Maybe we could get back on the other 5. Yeah. It's because of this thing right here, the cumulative case ratio per 100,000 people. This thing is not comparable to an epidemic suitability because the way that we find it is the reported case. The people are, what do I say? People are sick from the mosquitoes, so they report it to the hospital and then they record it. Those people could be the same, you know, in reality, like I said, they become sick, they recover, and they could become sick again. So it could be the same people. And they're not in the same scales. So that's why they're not in the same scales. What the C-score does is basically calculate the scale from itself, from its own province. So in the cumulative case ratio, they calculate through their own 77 province, their means and standard deviation to each specific province to see which one had the highest intensities. So we do the same. We can do the same for the Tmax, Tmean, and Tmean. That's why we did all of it to see just the intensity on the province and use those information for mean square errors.
Maybe I'm busy, but did you compare with your result that actually?
Did I compare my result with my actual data? Yes, that is the actual data, the cumulative case ratio. Okay, I'm just going to explain this. So this is the cumulative case ratio. So, and I'm calling that I add them all up as a single reported case. Here you have 194. Then divide it by the means of population type of province. Divide them all up and get this. Then, since I have the information already, I average them all up. Not the same, not for developments. No, it's very wrong. It's very wrong. It's very wrong. And the reason for that could be the immunity, or like population size. We don't know, but we could replicate that. Okay, everyone don't have any more questions, right? Should we end this? Yeah, we could end this, yeah. So, yay!